Guys, welcome back to my channel, and today we are going to look at Hedetniemi's conjecture, and this is part of graph coloring concept, graph coloring and chromatic number. Okay. Okay, so before going further into what is Hedetniemi's conjecture in mathematical terms, we will first look into a real world sample analogy that explains what Hedetniemi's conjecture is in real life and then look at it mathematically. So if you guys are new to graph coloring concept and you don't know what chromatic number is or represents, you can check out the part 1 of graph coloring. There I have explained with the prisoners being assigned how many prisons has to be assigned to prisoners who don't like each other. That question, through that I have explained what chromatic number is. You can go through that. So first, quickly let us we can recap what chromatic number is. I will not go in very deep explanation. Okay, so suppose this is a graph. Okay, and the nodes represents the vertices, the dots or the nodes. They represent something in the real world. For example, we can say these represents exam subjects, final exam subjects. This is subject 1, this is subject 2, this is subject 3, this is subject 4. And some if there is an edge between two subjects, when at least one student has taken both the subjects, so they cannot be conducted at the same time concurrently on the same day. So we have to that means S1 and S2 has to be conducted at different times. Okay, then only the students who have taken both the subjects can give the exams. Okay, so how many minimum time slots do we require to conduct the exams for all the 4 subjects? We require the minimum time slots that would be representing by graph coloring, where adjacent nodes cannot have the same colors. Suppose S1 I give the color 1, then S2 cannot have 1, but S3, as S1 and S2 does not have an edge, that can be given the color, same color blue. Okay, and S1 and S4 also don't have an edge, so I can give the same color blue, but S2 I have to choose a different color, so I will give it the red color. Okay, so see, S1 S2 they don't have same colors, S2 S3 not, they don't have same color, but S3 S4 has been assigned the same color, so I have to change the color. Now as I want the minimum time slots, these colors they represent different time slots. I have not used, I can reuse red's time slot again. So what does this mean? That S2 and S4 will be conducted at the same day and same time, and S1 and S3 subject exams will be conducted on the same day and same time. Okay, blue colored will be on same time slot and red colored would be same time slots. Okay, this is the minimum we require 2 time slots, that is nothing but the chromatic number of the graph G. Okay, so we have recapped what chromatic number is. Now let's go and look at the analogy for Hedetniemi's conjecture. Okay, so the problem is like this. Okay, so you want to conduct weekend parties, okay, for your friends. You want to invite some of your friends on, you have 4 weekends in total, or next month also weekends you can take and conduct parties or get-togethers in such a way that you call only those people who you think will have something in common to talk about. Okay, so what information do you have? Let us see. So we will move on to a new page. Okay, so you have 2 kinds of information with you. two graph informations. First, I will tell you, you have information. This G graph represents information about their jobs. Okay. And we know that if we will take the example and then see. See, one is an economist. Okay. And wait, I will not draw the vertices right now. Okay. One is an economist, and one of your friend is a teacher. One is a camp counselor, camp counselor, and is a math professor, math prof. Okay. We know that because of the occupation, the math professor and the economist will have something common to talk about. Similarly, the math professor and the teacher, as they are both in teaching profession, will have something common topic to talk about. But the economist and the teacher and the camp counselor and the economist, they are in totally different professions, so they don't have anything common to break the ice to talk about. So the people who have nothing, absolutely nothing common to talk about because of their professions, I will connect them with an edge. We cannot call them on the same weekend party. Okay. Similarly, economist and camp counselor will have nothing common to talk about. The camp counselor and math professor will have nothing common to talk about because of their professions. So now, how many minimum weekends parties we need to call these people based on this information, so that we call only those people who have something in common to talk about, or they don't have an edge. Okay, if they have an edge, they have to be called on separate weekends. Okay, let's say we call the teacher on weekend colored by yellow color, then the economist cannot be called over there. We will call him on the weekend we color with blue. Now, the camp counselor, we cannot call on blue weekend, but we can call him on yellow weekend as it does not have an edge over there. So we are calling camp counselor on yellow weekend. And the math professor cannot be called on yellow weekend, so we will call him on the blue weekend. Okay, so we can mark two weekends, one of them yellow and we one of them blue, and the other weekend uh, with a yellow color. Okay, so all the people we marked with blue color will be called on blue weekend party. They are compatible, and all the people who have been colored yellow, they can be called on yellow weekend party. Okay, so let's move ahead. Now, second information, you have another information about your friends, very important information. This graph we are calling H, and this is called the hobby information. Okay, the hobby information, that some people are stamp collectors. So from now onward, I will write stamp collector as SC. Okay. And you have a yoga instructor. So yoga, some people do yoga. We will write in short as Y. And some of your friends, they do meditation as a hobby. So we know that stamp collector will not have anything to common to talk about with the people who do yoga or who do meditation, but yoga and meditation, they do have something to common topic to talk about. So how many minimum weekends parties we need to throw to call these people? Suppose stamp collectors I'm calling on green weekend. Okay, then the yoga and meditation, they have to be called on a separate weekend. We will give now which color? Say white color. Okay. So we see the chromatic number for both the graphs. For the job graph, based on job, if we throw the weekend parties, then how many parties we need? The chromatic number of graph G is 2. 2 weekends we need if we call your friends like based on job. And if based on only hobbies, we throw the party. Here also the chromatic number of this graph, minimum weekends we need to throw such a party, would be 2. Okay. All right. Now, the next question is, suppose you want to call your friends based on both these information, both hobby and job information. You want to make a graph that combines both the information and see, can you throw the parties in less than 2 weekends? This is the problem that the conjecture deals with. Okay, now we will combine the jobs with their hobbies. So we saw we had 4 kinds of jobs, and every person along with the job, they can have one of the 3 hobbies. So for each of the, if we combine the information, we will have, for each job we will have 3 kinds of hobbies. Okay, so I'm writing in short form. The economist E can be a stamp collector. The economist E can be a can have a hobby of doing yoga, and the economist can have a hobby of doing meditation. Similarly, the teacher can have a hobby of I'm writing the T, teacher with T. Okay, the teacher can be a stamp collector. Okay, in after oblique I'm writing the hobby. The teacher can do yoga as a hobby. The teacher can have meditation as a hobby. Okay, and then the camp counselor, I'm writing as CC, can have stamp collecting hobby. Okay, stamp collecting hobby, or they can have yoga hobby, or they can have meditation as hobby. And similarly, the math professor MP can have a stamp collecting hobby, or yoga or meditation hobby. So this combined both the graphs, when you are combining or storing 2 informations, then this type of graph is known as tensor, or a kind of a product of the 2 graphs. Okay, now we saw that in the job graph, the teacher and the economist were not compatible jobs, right? They have nothing in common to talk about. But now you see, the if they have one thing common, at least one topic common to talk about, the teacher can, having a hobby of stamp collecting, can talk with economist having the hobby of stamp collecting. So if they have either job or a hobby in common, then they can be called in the same weekend party. So thus combining do information reduce the number of the parties, or the number of colors you need. uh, does it reduce it or increase it, is what it the conjecture deals with. Okay, let us make the graph quickly. Okay, I know that economists, they have nothing in common, absolutely common with the teachers, but the stamp collector, they can be called together, so they don't have an edge. But the economist having stamp collecting hobby has absolutely nothing with teacher doing yoga, or teacher having meditation as hobby. Similarly, the economist having yoga, meditation as hobby, they will not have anything in common with stamp collecting, absolutely nothing. Similarly, there's a camp counselor and economist job, they didn't have anything in common. So uh, absolutely nothing in common with the camp counselor job will be economist having stamp collecting as hobby, and then the meditation. Okay, we'll use a small eraser. Okay, so let me quickly finish uh, drawing the graph like this. Okay, then this And okay, this and this. We had only two edges over here, yeah. And okay, this and this will be also joined, right? Okay, all right. Then we have to check on camp counselor. Camp counselor and the economist we have already joined. Camp counselor and math professor we have to join like this. This looks like a very complicated graph. Okay. Um, yeah. And these two have nothing in common. Okay. Now, math professor, okay, we have made. Teacher also we have made. So we have finished the. So this is what the final tensor graph, yani G cross H looks like. Now the question is same, how many minimum colors do you need to color this graph so that adjacent nodes don't have the same colors? Okay, so one of the ways we can color is this. We know the individual colorings, graph colorings, right? G and H graphs, we know the G graph requires two colorings, and the hobby graph also required minimum two colors, right? So what we can do is one algorithm, the lazy algorithm could be that we can call all the teachers and camp counselor based on the only looking at the job. We can call all the teachers and camp counselors with the same color, and all the economist and maths professor with the same colors based on the both the only the job graph. Okay, so what we can do is all the teachers and the camp counselors we can make the same color. So teacher and the camp counselor, all the teachers we are coloring blue, and all the camp counselors we are coloring blue. Okay, and all the economist and maths professor they will be having based on only on the job. We are now calling based on only on the jobs. Okay, and we are ignoring the hobby at we are ignoring the hobby information. Okay, so what the problem with this is, uh, the teachers were not compatible with the economists based on job, but the teachers, the teachers doing yoga, teachers doing meditation, uh, can be called on the same party, weekend party, as such as the economist doing yoga and economist doing meditation. So actually, we can. It is possible that there exists a graph, a tensor graph, G cross H graph, where you require lesser than the two colors. Okay, we can combine the people with the not compatible jobs but having the same hobbies or compatible hobbies on the same weekend party. Similarly, in some of the problems what can happen, you cannot make conclusions based on uh, the individual G and H graphs. Okay, cause the combined graph can become more complex, and the constraint based on the constraint, the chromatic number of the combined graph, because we have two informations. So making conclusions based on only one of the graphs means you are ignoring the second information that might help you reduce the chromatic number of the combined graph, right? Because if we colored based on only colorings of graph G or jobs, and we ignored the fact completely that they can have common hobbies as well, so that might help you reduce the chromatic number of G cross H. So we will write in mathematics terms now. The conjecture says that the chromatic number of G and a G cross H, or the tensor graph, is equal to the minimum of either chromatic number of G, comma, chromatic number of graph H. So whichever graph has a minimum chromatic number, uh, based on, well, it means the if the chromatic number of the hobby graph was lesser than the job graph, we can have a big graph. This was a small example. If the chromatic number based on the hobbies was lesser, then directly based on hobbies you can color the uh, combined information graph, and that would be the minimum, but that is not necessary. So this conjecture is false. Okay, hope you like the video. Please subscribe to my channel and share it with your friends, and keep exploring and different applications, and happy learning. Bye bye, take care.